All right, let's take a look at why these trends in atomic size exist. So remember our periodic table here. We said that this top right was the smallest. So let's go ahead and take a look at the trends. So we have to take a look at kind of the vertical and the horizontal trends. So let's take a look at the vertical one first. Right, by vertical, what I mean is what happens when we go up the periodic table, right? We said this was small up here, and this is big right here. So think about what happens as we're going up here. This over here is like n equals 1, this is n equals 2, n equals 3, n equals 4, so on and so forth, right? So think about what that means if you think about the Bohr model of the atom, or even the quantum mechanical look at it, right? We said as n is the general size of the atom, right? So this is something like n equals 1. And then this would be something like, n equals 1, right? Up to n equals 2. And then we get bigger and bigger and bigger, right? N equals 3. So as we go down the periodic table, we get bigger and bigger, right? So this is small, this is large. As n increases, the atom size increases. That one's pretty simple, pretty logical, pretty easy to figure out. Let's take a look at the horizontal side of things. And when we go from left to right, we get smaller, right? So this is small, this is big. So let's think about that. And if we look at our periodic table, let's take a look at lithium and neon, for example. So you can use this periodic table. If you hit this tab up here that says properties, you can look at different properties. So let's see, go calculated radius, right? You can see lithium has a radius of 167 picometers, tells you right there, highlighted in yellow. And neon has one of 38 picometers. So lithium is way bigger, about maybe 4 or 5 times the size. So let's take a look at what's going on there. Let's think about lithium and neon in kind of the Bohr model-esque. So we'll make lithium big since it is big. And if we think about the electron configuration of lithium, it's going to be 1s2, 2s1. So you'll have 2 electrons on this n equals 1, and then 1 electron on this n equals 2. If we think about neon, it's going to have 2 electrons in its n equals 1 orbital, and then 8 electrons in its n equals 2 orbital. So 2 electrons there. And then this filled outer shell. So 1, 2, 3, 4, 5, 6, 7, 8. And let's go ahead and just make it even smaller, just to kind of be more accurate there. So it kind of looks weird at first look. You're thinking neon has more electrons. Why is it smaller? Well, we have to think about what's going on in the nucleus as well. Remember lithium here. Lithium is the 3rd element, so it has 3 protons. Neon, the 10th element over here, it's going to have 10 protons. And remember shielding. We learned about shielding. And when we learned about shielding, what we said was that inner electrons shield outer electrons from the pool of the nucleus. Right, but only if they're in a lower n. So they only shield when they're in a lower n. And so this leads to a very important concept that you're going to want to understand very well, because it's going to explain some of the other trends and properties we see, and that's called effective nuclear charge. It gets the symbol Z with a subscript of effective, so ZF, and it's equal to Z minus shielding electrons. Right, so this part right here is effective nuclear charge. This right here is number of protons. And this shielding electrons are inner electrons. So Z effective is the pull that outer electrons feel. So they feel the pull of the protons in the middle minus shielding electrons. So let's think about what we have in our model of lithium and neon. If you think about what the Z effective here is, lithium has 3 protons, and then it's got 2 inner electrons, right? So both of these 2 inner electrons are going to repel this outer electron, so it'll be 3 minus 2 for a plus 1. So this electron here feels a pull of approximately plus 1. Right, plus 1. Whereas here we think about these outer electrons. Neon's going to have 10 protons, and then the only electrons that are shielding are the inner electrons, right? Only the inner electrons. And so there's only 2 of them, and so each of these outer electrons are going to feel a pull of plus 8. And so if you're thinking about which one's pulling harder, plus 8 is obviously going to pull harder than plus 1. The harder you pull on these electrons, the closer they'll get to the nucleus, and thus overall smaller atom. And so you can use these two properties, the horizontal and the vertical kind of look, to explain the trends in size. And then finally, transition metals, we said they don't really follow this trend, and that kind of makes sense as well if you think about where their electrons are going. So transition metals are going to have electron configuration of something like ns2 n-1 d, and there's going to be some number of these electrons. And so you can see we're not really adding electrons to the outer shell. We're kind of more so adding so-called core electrons. So that kind of does actually explain the size of transition metals as well.